Hi, the topic is articulation point and bi-connected components. So let us know first what is an articulation point. In a graph, if there is any vertex whose removal will disconnect the graph into multiple components, then that vertex is called as articulation point. In this graph, I have taken an example. This 3 is a vertex. If you remove this 3, then this 1, 4 and 2 will form one piece, that is one component. 5 and 6 will form another component if I remove this 3. That's how 3 is an articulation point. If a graph is representing some network, road network or computer networks, then we don't want any articulation point. If that articulation point is having any problem, then the network will break into multiple components. Even if anything is failing in the network also, network should remain as intact as a one single component. So that is the problem of articulation point. So we prefer that articulation point should not be there in the graph. If there is an articulation point, we will like to remove that articulation point. So the solution is, if you know what are the components in this one, like I can directly see that 1, 4 and 2 and 5, 6 are two different components. Just join an edge between them. If you connect an edge, now there is no articulation point in the graph. If you remove 3 also, this 5, 6 will be connected via 4. And if 4 is also removed, the probability that multiple nodes are failing is less, right? So anyway, if 3 is removed, then the graph will not break into multiple pieces. So there is no articulation point. So how to remove articulation point? Connect the components with an edge. That's all about articulation point. Now we want a procedure to find out articulation point. Just by looking at a graph, we are able to see this one, but how our computers or machines can do that. So for that, there should be a procedure or an algorithm. So now I will explain you the algorithm for finding articulation point. So the procedure is, first step, prepare a depth first search spanning tree for this graph. So first prepare a depth first search spanning tree. So I don't want result, I want spanning tree. So if I start from vertex 1, then I can go on vertex 4, then from there I will go to vertex 3, then I will go to vertex 5. From there, I will go to vertex 6, and from 6, there is an edge to 3. Now, there is no more connected vertices for 6. Come back to 5 and come back to 3. From 3, there is a vertex that is 2, and from 2, there is an edge to 1. And 2, there is no more vertices connected. 3 also nothing is connected. 4 also nothing is adjacent to it. So 4 is completely explored. 1 is also explored. So all are explored now. This is the depth first search spanning tree I got. This is the first step. We are finding articulation point. Now for this depth first search tree, mention discovery time or depth first search number for each vertex in the order in which they are visited. So depth first search number, I'll write just D. D is 1. Then discovery time is 2. Discovery time was 3. Next, this we have visited. So discovery time is 4 and discovery time is 5. And discovery time of this one is 6. So this is the order in which the vertices are visited. So if I write the vertices 1, 2, 3, 4, 5, 6, then their discovery times are 1, 2 is 6, then 3 was visited at 3, and 4 at 2, 5 at 4 and 6 and 5. 5 at 4 and 6 at 5. These are the discovery times. Next step. Now we have to find out the lowest discovery number or depth first search number reachable from any vertex by taking one back edge. So these are called as actually back edge. So from 1, I can go to descendants and take this 2 and come back here. So from 1, lowest number is 1 only. Then from 2, the lowest number that is reachable from 2 is D, 1, right? From 3, I can go to 2 and then to 1. So 1. So this means that what we are trying to find out is there is some path that is going back to the parent, right? From 3, if I go downwards also, there is a path to the parent. Then for 4, from 4 I can go to 3, then 2, then I can take a bracket. So the lowest number reachable is 1. Then for 5, I can go to 6 and then I can come back to 3. So this is 3. And for 6, the lowest depth first search number is 3. This is 3. So for 5 and 6, it is 3. Now the next step is to find out articulation point. So for that, the condition is, if there are two vertices u and v, where u is a parent and v is a child as per this depth first search spanning tree. If there are two vertices, means one is parent, one is child. So this is parent, this is child, this is parent, this is child, this is parent. So there are many pair of vertices which are satisfying this relationship. Then the lowest number of v, if it is greater than or equal to d number of u. If the lowest number of some vertex is greater or equal to the depth first search or discovery number of its parent, then u is an articulation point. U will be an articulation point. So if this condition is true, then u is an articulation point, and this condition is for all the vertices except root, right? This will not work for root. So leaving root, let us check other vertices. 3 and 4. So what is the lowest number of 3? 3 is a child, right? Lowest number of 3 is 1. And what is the discovery number of 4? Depth first search number of 4? It is 2. So this is 1 and this is 2. So no, this is not greater or equal. Then let us take next vertex, 3 and 5. So let us say this is 3 and this is 5. So L of 5 and D of U. So D of 3, what is D of 3? D of 3 is 3. And L of 5, lowest number of 5 is 3. Oh, this is greater or equal. So yes. So who is an articulation point here? 3 is an articulation point. 3 is an articulation point. So this is an algorithm for finding articulation point. So you can write up algorithm for this one to perform depth first search and also maintain depth first search number. If whenever you are getting any back edge, so maintain the lowest number also. So this you can write on a program or an algorithm for this one. Then after generating these two arrays, we can compare whether any condition is true here. If any of such condition is true, then that vertex is an articulation point. So our algorithm can find out articulation point. Our program can find out articulation point. And if any articulation point is found, then we connect an edge in between two components, right? From that articulation point, the one side is one component, the other side is another component. We can add an edge between them. So for making a graph stronger by removing an articulation point, we use this procedure. We find out the articulation point and add an edge to remove articulation point. Now the last thing, for the root, this condition will not be true, right? Then if root is an articulation point, because the traversal can start from anywhere, then how do you know if root is an articulation point? See here, root is having only one child. If suppose root is having one more child, some vertex is coming here, then if root is having multiple children, then root is an articulation point. This is a different condition for root, right? So that's all about biconnected components and articulation point.